Hi everyone, our presentation is on afterburner design of jet engines. I'm Ethan Mercado and my group mates are Nicholas Jensen and Jonathan Hood. So what are afterburners? Afterburners are a component used in jet engines to increase thrust, primarily found in military and supersonic aircraft. Thrust is increased due to the injection and combustion of fuel into the flow. It can be seen as an additional combustion chamber, and an afterburner can be found over here on the right. Additional fuel is ignited inside of the exhaust, creating an afterburn. So, history of afterburners. Afterburners were first developed during World War II to boost jet engine performance in military aircraft. The concept was inspired by turbojets but included a secondary combustion stage. Some key milestones were the introduction of afterburners in aircraft like the Concorde and F-4 Phantom. So in the 1940s, the Caproni CC-2 was the first aircraft that experimented with afterburners. In the 50s, Lockheed Martin F-94 Starfire was the first operational afterburner. In 1969, Concorde had the first civil use of afterburners. And then in the 1970s, variable area nozzles to improve thrust control were introduced. And then in the 1990s, a focus on reduction in emissions and noise impacts. So the first afterburners in Italy, the Caproni CC-2 was the first aircraft to incorporate and fly with an afterburner. It can be seen here being tested. The back is taken off. That's the afterburner burning. 1943, in the U.S., the National Advisory Committee for Aeronautics, NACA, the predecessor to NASA, began testing an afterburner fitted onto a General Electric IA engine. In 1946, the U.S. Aircraft Engine Research Laboratory achieved thrust gains on the General Electric TG-180 engine in the altitude wind tunnel, which can be seen over here on the right. That's the TG-180 right there. And then in 1949, Pratt & Whitney developed the first mass-produced afterburning turbojet, the J-57. Can be found on the B-52 bomber and a lot of older aircraft. So this is the Pratt & Whitney J-57. It was the first engine with afterburner to be mass-produced in the 1950s. It's found on the F-100 Super Sabre, the B-52 Stratofortress, and Lockheed U-2. It produces a thrust of 52 kilonewtons without afterburn, but the afterburner increases the thrust to 76.5 kilonewtons. Here we have a picture of the J-57, and below it is a schematic. You can see the turbine here with the afterburning stage following it with these fuel injectors to add additional fuel into the exhaust, creating the burn. Here we have a F-100 Super Sabre with the J-57 afterburner taking off, and that's the afterburner there. And I'll go ahead and show a little clip of this aircraft taking off. As you can see in the video, the afterburner reduces the takeoff time, and we'll get into that in this slide. So why use an afterburner? Afterburners increase the efficiency of jet engines by burning additional fuel in the exhaust, boosting thrust without the need for a bigger engine. The process adds extra fuel to the high temperature exhaust gases, igniting them to create a higher velocity exhaust. How thrust is increased. Adding more energy to the exhaust stream leads to higher exit velocity and thus more thrust. And as you can see on the graph on the right, to achieve the same altitude in less time, an afterburner will greatly reduce the time. And you can see in the video I played before how fast that Super Sabre took off. Afterburner function, so flow coming out of the turbine exit is slowed down to allow for stable combustion. Fuel is mixed in with the stream and turbulent currents. An igniter provides a stable combustion, and bypass flow keeps the jet pipe from reaching melting point temperatures. And you can see here by the schematic, these little fuel injectors, these are called V-gutters, and they help stabilize the flow and ignite the fuel to provide additional thrust. So temperature and entropy. Without an afterburner, standard Brayton cycle for a jet engine, temperature decreases after flow leaves the turbine and no additional thrust. And here we have the traditional Brayton cycle. You can see temperature decreases. But with an afterburner, the Brayton cycle is modified as flow leaves the turbine, as additional fuel is ignited in the afterburner. Temperature is increased and entropy and velocity also increase. This creates additional thrust, and as you can see here, temperature decreases after it leaves the turbine, but as fuel is added into the afterburner, it increases along with entropy and velocity, creating more thrust.
So looking at turbojets with afterburners, in the older aircraft, they used turbojets instead of turbofans to maximize the speed. Turbojets directed all flow through the engine core, where it is compressed, combusted, and expelled at high speeds. Turbojets are not as fuel efficient at low speeds, and early fighter jets such as the F-4 Phantom II and the F-104 Starfighter used turbojets with afterburners. On the right, we can see the Lockheed F-104 Starfighter. That is an aircraft that used turbojets with an afterburner. For turbofans with afterburners, modern aircraft use turbofans instead of turbojets because they have better fuel efficiency while maintaining speed. Turbojets use a large fan at the front of the engine to bypass air around the core, creating more thrust with lower fuel consumption. Turbofans generate thrust from both the core exhaust and bypass air, and modern fighter jets like the F-35 and F-22 use turbofans with afterburners to achieve supersonic speeds and fast takeoffs. On the right, we can see the Lockheed Martin F-22 with afterburner, and you can see the afterburning effects at the exit of the nozzle on the right side. So in this video, you can see the effects of the afterburner physically with the bright glowing flames coming out of the nozzle. And once the vehicle reaches a certain height at the end of the video, you can see the afterburning turning off. So looking at fuel-air mixing, the uncombusted oxygen from exiting the flow provides further combustion with the fuel that is injected and then ignited. Exiting flow from the turbine is too fast for the fuel to combust, and it'll blow away before it's even combusted at the high speeds coming out of the turbine. Vapor gutters or V-gutters are then used prior to the fuel injection to spin the jets into turbulent eddy currents. On the right side, you can see what the eddy currents look like as in going over the flow of a cylinder. These currents then slow down the high-speed flow and allow fuel to mix better with the stream with stable combustion. Looking at the flame holders in the V-gutter, V-gutters are flame holders. V-gutter flame holders are the most commonly used in afterburners. The V-shape creates low-pressure wakes where the hot gases recirculate, such as the eddy currents that I just talked about. It also allows the fuel to ignite and stay lit based on its geometry. Looking at some afterburner enhancements, more specifically the nozzles. The variable area nozzle, it varies the exit area to control the pressure ratio across the turbine. So when there's more afterburning being done, there's a greater pressure buildup, and then due to the greater pressure buildup, a larger nozzle area is required, which the variable area nozzle is able to adapt. The two-position nozzle features two eyelids that can move independent of each other, and they can also be moved to close or open the nozzle area as well. So it's kind of just like a secondary option or type of nozzle. Looking at the material selection, The afterburner components are subjected to very high temperatures that materials need to be able to withstand. Some challenges that come from material selection is the thermal expansion, some oxidation, and the risk of material fatigue due to these repeated high temperatures. Some common materials that are used are materials that have high heat resistance and durability, such as superalloys, ceramics, and advanced composites. Looking at the picture on the right is an F-16 Falcon F-100 with ceramic composite seals shown in the 5 yellow arrows above. These were replacing superalloys that are currently used, and this was for a test fire. So what makes an effective afterburner? So fuel-air mixing is one of these. It's proper mixing of fuel with the exhaust air, and it is crucial to ensure that fuel is evenly distributed for the complete combustion. Flame stabilization, and that's the maintaining stable combustion, is key to preventing backfiring, which is when the pressure at the exit is too high. The pressure in the nozzle itself is too high compared to the turbine exit, and then the pressure pushes back and forward through the system, or unstable engine operation. Looking at space efficiency, afterburners are compact, and they require efficient integration within the engine's overall design. Looking at the trade-offs, first up is the efficiency versus the thrust. So increasing the thrust often comes at the cost of fuel efficiency. Looking at weight versus performance, adding materials for durability or more advanced features can increase weight, which then affects the overall aircraft performance. And then for noise versus environment, significant noise levels are produced, and they need to be considered in civilian applications such as the Concorde or environmental regulations. So for the conclusion, afterburners play a crucial role in the design and performance of high-speed aircraft, offering significant increases in thrust at the expense of efficiency. Balancing design considerations such as fuel-air mixing, flame stabilization, nozzle design, and material selection is essential to ensure an effective afterburner. Ongoing advancements in technology aim to improve the efficiency, durability, and environmental impact of afterburners. Thank you. Is there any questions?